At the dawn of the machine age, a new kind of titan began to rise in factories across the world. Giant hydraulic forging presses. Some were so large they made grown men look like many action figures beside them, towering as high as 8 stories tall and anchored deep into the concrete and bedrock. They didn't feel like machines, they felt like buildings. In a single stroke, they could drive incredible force into the red-hot steel. As the workers stood only a few steps away, they could feel the heat and the vibration through the floor. But when the press started to close, there was no warning signal and no way to stop it. Only a few feet and a few seconds separated the men from thousands of tons of crushing force. This is the story of the hydraulic forging press giants. Fortunes were made, lives were crushed, and their surprising role in the Cold War helped shape the world that followed. To understand why the press was even built, you have to start with the failures that no one else could see. In the mid-1800s, factories faced limits that their existing tools could not solve. Steel parts were getting thicker and larger, but the old existing methods only worked on the surface, which ultimately left hidden flaws that would eventually show up later on. Steam hammers were powerful but not consistent. They shook entire buildings and tired out the workers nearby. And even after countless blows, cracks from the hammer strikes could still form deep inside the rails, artillery and ship parts, setting up failures that arrived after the work was already considered to be finished. That problem forced a different kind of thinking. In 1795, Joseph Bramah proposed a new idea using liquid pressure, rather than impact to apply force. The point wasn't just power, there was control, allowing pressure to be applied evenly and steadily instead of through repeated hits. And in the 1860s, engineers like John Howell started using this idea for forging. One steady press could drive heat and pressure through an entire steel block, enhancing the internal structure instead of only shaping the outside. This change happened out of necessity, not just for improvement. Railroads were expanding, artillery was growing heavier, ships were getting larger, and the demand was for parts with fewer hidden flaws and less wasted material. Speaking of necessity and improvement, if these kind of industrial stories are something that you enjoy, I'd be truly grateful if you could subscribe and let me know in the comments what kind of stories or disasters that I should investigate next. Now, let's get back to the action. Early forging presses could apply several thousand tons of force in one controlled motion. They reduced extra machining, they cut waste, and they made parts more reliable, giving factory owners a practical way to keep up with the demand. But they also created a new kind of risk, because this time, the force didn't arrive as blows that you could anticipate, like that of a steam hammer. Instead, it arrived as one continuous closing motion. And once it started, it didn't stop. And that single change rewrote the forge floor because the violence didn't vanish. It just became more controlled. By the 1880s, that control was no longer an idea. It was steel, concrete and pressure, all scaled to industrial size. Forge shops had machines larger than the buildings themselves. Steam hammers weighing more than 1,000 tons ran day and night, cracking walls, loosening bolts and placing constant strain on the men who worked beside them. The hydraulic forging press marked a clear break from that approach. It didn't rely on repeated impacts. Instead, it pressed down in a steady, controlled motion made from enormous steel castings, some weighing hundreds of tons. The press itself needed special equipment just to assemble it. Now, the force came from pressure and not just movement. Hydraulic systems stored energy inside sealed cylinders, building up thousands of pounds per square in before anything moved. And when that pressure was released, it acted evenly, without the shock or the noise of a hammer blow. One single press stroke could do the work of dozens of hammer impacts, shaping a hot steel block in one smooth action. By the late 1800s, some factories eliminated entire rows of hammers, making forgings with fewer hidden flaws and far less waste. But this method brought new risks. In cold weather or under heavy loads, hydraulic systems could freeze or get stuck. Workers were sometimes forced to heat pipes, loosen fittings, or work near stored pressure that had not yet been released. As hammering faded, forge floors definitely became quieter, but the new dangers were harder to spot. The force was no longer sudden or loud, but constant and concealed, working silently inside spaces built around thousands of tons of steel and stored energy. And once factories committed to that kind of force, they had to do something even harder than building the press. They had to build the ground beneath it. The press wasn't just installed inside a factory. The entire factory basically had to be rebuilt into a foundation. By the early 1900s, the main challenge was not just building the forging press, but keeping it stable once it was fully assembled. The weight made regular factory floors unusable, so the first work wasn't skill at all. It was excavation. Builders had to dig deep foundations before installing any major parts. Some presses stood over 80 feet above the floor, with another 30 feet below ground. That wasn't over-engineering. It was the minimum requirement for stability. These lower parts were set in concrete and bedrock because lighter foundations cannot hold the structure once force was applied. Factories had no choice but to adapt to this. In many cases, the press became the center around which the entire plant was designed, with walls, cranes, and power systems arranged to support a single fixed machine. The building didn't house the press. The building starved it. Structural integrity depended on massive vertical columns, with each as wide as a large tree and longer than most residential buildings. Forged from alloy steel, these columns were heat-treated in furnaces exceeding 100 feet in length to ensure they could withstand sustained loads without failure. But a single mistake meant the whole structure could fail. So precision was required for every step. A flaw hidden in one column could bend frames, crack foundations, or send force into areas not meant to withstand it. And the frightening part was that you wouldn't always know until the press finally took a full load. And as for the workers, well, you could understand that they knew the risks early on. They watched as hundreds of tons of molten steel were poured into molds, knowing the machine being built would soon dominate the space and test the ground itself. The press wasn't simply installed on a site. It was permanently anchored to the earth, a necessity because of its size, not by choice. Once it was set, everything that followed had to live with it, including the men. And when the giants finally stood tall, the next question wasn't whether or not they worked. It was deciding who was allowed to control them. By the 1950s, the scale was no longer experimental. It was operational and run by a human hand. Control inside the forge had been reduced to a single point. At facilities such as Air Force Plant 47 in Cleveland, one operator remained at the controls of the machine, capable of forces that no human body could withstand. The control mechanism looks simple. Engineers later said the press responds instantly and precisely to the lone operator's hand on a lever just 3 inches long. And that was the unsettling part. This shows how little effort it took to control so much power. That small movement controlled a system capable of exerting up to 50,000 tons of force. 50,000! Around it were huge pots, nuts over 50 in wide, some weighing more than 50 tons, and single pieces heavier than whole workshops from the 19th century. Scale like that changes what normal even means. Once the pressure started, it could not be stopped. The press moved steadily, squeezing hot steel as workers watched from a safe distance. It didn't slam, it didn't shout, it simply kept closing. Okay, talk to me. Do you have any experience operating or working around these incredible machines? If so, please let me know in the comments so we can recognize who the real hero of this story is. The operator didn't need to use any strength to control the press. He guided it, trusting every valve, seal, and casting to work as designed so he could stay in control. But the system didn't care about his confidence. It cared about tolerances. So, inside the press hall, the quiet stood out. Thousands of tons moved at the touch of a tiny 3-inch lever, and everyone knew how close things were to going out of control. And if something failed, it wouldn't fail loudly at first. It would fail silently until there was no room left to move. But the operator wasn't the one who was closest to the danger. The closest men were the ones who had to step underneath it. The lever controlled the force. The floor crew lived inside its timing. The most dangerous place in a forge was no longer the furnace. Instead, it was the area right under the press. When the dies were open, the gap could stretch over 15 feet, and the cable below was as long as a railroad car. It looked like space, but in reality, it behaved like a trap. In that area, workers moved hot steel into place using hand signals while shouting instructions. They stood just a few steps from the die faces, knowing that once the press started, there was no real way to escape or stop it. They weren't just watching a machine, they were timing it with precision as if their lives depended on it. The work followed a set routine. Steel was heated, pressed, reheated, and pressed again, sometimes several times in one job. Pumps filled accumulators, valves were checked, and every step had to happen in the right order to keep things under control. And the routine only felt safe because it was familiar. This careful coordination was just as important for safety as it was for getting the job done. But the margin was thin. One mistake in timing could trap a hand, a tool, or even a whole worker between moving parts that would not stop no matter what. Once it started, it finished. An oral history from Bethlehem Steel later summed up the situation. A safety leader said that safety measures only worked when management backed them. Otherwise, they were just words. While workers continued to face dangerous conditions because the press didn't negotiate. Only the schedules did. The press didn't care how experienced someone was. It worked only based on position and force. To work safely under the dies, workers had to follow procedures, communicate clearly, and trust that the systems would work as they should. And trust was the most fragile part of the whole setup. And when the press closed, everything went quiet again. Workers waited for it to open, making sure the cycle had finished as it should, because the next move was always the same. Step back in, line it up, and hope nothing had changed. And yet, even with all that risk, demand didn't slow down. It escalated because once industry tasted what these presses could do, it wanted even bigger parts. As leaders across multiple industries realized what large forging presses could do, factories became less cautious. Many sectors began changing, having made things, focusing on larger, more demanding parts that older forging methods can no longer handle. The presses didn't just improve production. They quite literally reset the definition of normal. Aviation was one of the first industries to make this shift. Press-forged parts spread out stress along their internal grain so they could bend under pressure without breaking. By the 1930s, aircraft makers were ordering forgings that weighed tens of thousands of pounds before machining, which only large presses could produce. And once a design depends on a single forging, the forging becomes non-negotiable. That dependence quickly shaped the rest of the production chain. Once an airframe was designed around a large forging, the manufacturer cannot simply substitute smaller parts without redesign, retesting, and new tooling. The press did not just make the part. It dictated the geometry, the schedule, and the entire supply chain behind it. Civilian shipbuilding and heavy manufacturing followed a similar pattern. Large presses supported critical components that benefited from fewer joints, fewer fasteners, and fewer separate pieces that could loosen or fail under repeated stress. Over time, companies invested in press capacity because it reduced rework, reduced scrap, and reduced the number of machining steps needed to reach final dimensions. But every efficiency came with the trade. Fewer alternatives when the press was down. As more industries adopted press-forged components, demand concentrated around a few plants that could supply them. By the mid-1950s, Air Force Plant 47 in Cleveland and Air Force Plant 63 in North Grafton were among the few places with 50,000-ton presses that were capable of producing the large forgings that civilian manufacturers were now designing around it. In civilian industry, the press was not a symbol, it was an obligation. And once the obligation exists, the next question isn't, how do we build bigger? It's what happens when the press stops, or when the pressure that's supposed to be controlled gets loose. The biggest danger in a forging shop is not the heat, but a hidden force. A hydraulic press may look still, yet it can hold enough pressure to bend steel and cause deadly injuries. It can technically be off and still be fully loaded. In the years between the World Wars, shops with large presses became more careful during work stoppages. Pump systems could build up and hold about 4,500 pounds per square inch of pressure and sealed pipes, storing energy behind valves and seals that gave no warning before failing. And the risk wasn't the motion you could see, it was the pressure that you couldn't. The area around the press was always risky. Some large presses had die tables about 12 by 26 feet, big enough to bring workers close and leave little room for mistakes. Once the press started to close, it kept going no matter who was nearby or how tired they were. The machine didn't read the room. It only followed the cycle. Accident reports from OSHA show a clear pattern. Workers were crushed while doing everyday tasks such as clearing scrap, lining up material, or making adjustments. These tasks turned deadly when stored pressure was released or the press started moving again. And as you might have guessed, they didn't happen during the dramatic moments. They happened during the routine ones. Investigations blame factors such as missed steps, poor guards, or equipment problems. But the result was always the same. The gap closed, and there was no time left. With a steam hammer, it makes lots of noise and moves, so you know when it's working. But a press moves with almost no warning. It works slowly and steadily, and once it stops, it keeps going until it finishes. That's what makes it so deceptive. It doesn't feel urgent until it's already too late, and that's what the reports can't fully capture. What it felt like to work beside a machine that could be deadly even while it looked calm. The numbers explain the pattern, but it was the workers who explained the decision to come back anyway. The men who work these machines understood how dangerous they were. Even so, they came to work each day, fully aware of the risks, not because the danger was invisible, but because it was familiar. At places like Bethlehem Steel, the workers felt both pride and a constant awareness of danger. One worker said, "I was very happy to work at Bethlehem Steel. I enjoyed the work." And this pride grew in an environment where mistake could have serious consequences. In the mid-10th century, some steel plants had tens of thousands of workers, all knowing that the press would not make exceptions for anyone. The rule was simple. The press didn't care who you were. Working at a large forging press was just not routine labor. It took years of experience and learning from others. Workers said the machines were quiet and controlled, but they were never forgiving. A former press operator remembered how different the press was from older machines, calling it quiet and uneventful compared to the steam hammers. The effortlessness of it is eerie. The machine's smooth operation showed just how powerful it was. Not that it was any less risky. If anything, the calm made it easier to forget what was loaded behind the metal. Years later, managers and supervisors still talked about how skilled and dedicated the forging crews were, calling them skilled, dedicated, and proud of their craft. The job required careful teamwork and following procedures, not just physical strength. In that whole, discipline mattered more than bravado. The press didn't reward the risk takers. The worked best for those who were disciplined and consistent. For workers who learned to respect these limits, finishing each shift safely became a mark of professionalism throughout their careers. Because the real achievement wasn't shaping steel, it was walking out at the end of the day. But pride didn't make the work safe. Safety came later, after the injuries stacked up and the excuses ran out. Forging presses were built for power and not safety. Most of the safeguards that were eventually added came only after accidents, and the injuries made it clear that they were needed. In other words, the rulebook was written in blood. Throughout much of the early 20th century, production priorities outweighed safety considerations. Protective guards were limited, procedures were loosely defined, and responsibility for safe operation often rested with foremen who relied on experience rather than formal guidance. That worked until it didn't. At places like Bethlehem Steel, the injuries added up over time. Many accounts actually describe workers who knew the risks, but also knew they were expected to keep up production. Yes, Safety meetings were held, but without steady support from top management, so they had little effect when deadlines got tight. When the schedule tightened, the margins disappeared first. A safety leader put it simply, "Now, it may take you a little bit longer to do it safely, but you're going to be way ahead of the guy who doesn't." And this comment came from hard experience, not from a training manual whose advice paid for by someone else's injury. In the 1940s and the 1950s, companies started adding physical barriers, lockout steps, and tighter rules for maintenance and adjustments. These changes often slowed down production, sometimes a little, sometimes a lot, and workers didn't always accept them right away because every safeguard was also an admission. The old way had been costing people's lives. But even with these changes, the presses were still dangerous. There was no way around that. These machines could deliver tens of thousands of tons of force, and they couldn't be made completely safe, only less risky. Following the safety rules was crucial, and breaking them still led to serious accidents. It didn't punish people for being reckless. It just punished them because they were too close. The safety measures that later came became standard, and they were not put in places of precaution. They were only added after people had already been hurt around machines that had long shown how dangerous they could be. And even then, the machine never changed. Only the rules around it did. But then the stakes changed again because these weren't just factory rules anymore. They became national priorities. The impact of these massive machines quickly spread beyond just industrial use. Once governments realized what large forging presses could make, the machines became important for more than just manufacturing. They became strategic. After World War II, investigators who studied captured German aircraft noticed a clear trend. The main forge parts were lighter, stronger, and more uniform than similar Allied parts since they were made as single pieces instead of being put together from several sections. It turns out this was standard practice for the Germans, and it meant something uncomfortable, that better aircraft could be coming from different parts of the world with better presses. These discoveries caused immediate worry. Intelligence soon showed that the Soviet Union had taken over Germany's biggest forging presses, including machines that could apply tens of thousands of tons of force. To American officials, this meant a major change in industrial power, not just the handover of equipment. So in the early 1950s, the United States started the heavy press program. One of the main machines was a closed die forging press with a 50,000-ton rating built at Air Force Plant 47 in Cleveland and put into use in 1955. The goal was not fast production, but controlled capability, the ability to make the largest aircraft parts on demand. These presses could shape aluminum and steel pieces weighing over 200,000 pounds before any machining. The finished parts were meant for bombers, transport planes, and future aircraft that were still in the design stage. In other words, the press was being built for planes that didn't exist yet. Because of this, the press itself became important in national defense planning, and keeping it running supported whole fleets. And when it went down, capability went down with it. But by then, forging presses were not just factory machines anymore. They quietly became part of military infrastructure, making parts that affected how far the aircraft could fly, how much they could carry, and how long they could stay in the air. Quietly, the forge became a frontline defense, and unlike planes or weapons, these machines didn't deploy. They stayed put, anchored, permanent, and waiting. That permanence is the final strange truth of the forging press. It was built to move metal, but can never move itself. Even after the workers who built their foundations were tired or died, the presses stayed where they were originally installed. Buildings grew up around them, and the layout of each space was shaped by machines that were never meant to be moved. They didn't just outlast the men, they outlasted the era. Each press was built from huge parts. Its frame used massive steel castings, sometimes so big that a whole foundry was needed just to make one piece. These parts were made to last for decades, not to be replaced often. Once the steel was set, it was meant to stay set. Work routines changed to fit this sense of permanence. In some factories, the press decided where walls went, how cranes moved, and where people could work safely. The factory had to adapt to the machine, showing the limit set by its size and its fixed spot. The press didn't fit the building. The building learned to fit the press. Operators today say their experiences are much like those of earlier workers. The presses still respond smoothly to their controls, closing steadily and needing just as much care and respect as before. The controls may feel effortless, but the consequences never did. These machines are quieter now than the old forging methods. They still move slowly and carefully, and people working nearby stay cautious, knowing that the same motion can still shape metal or cause serious harm. The danger didn't disappear.